Our paper is Action-Insensitive Embodied Visual Navigation. We will introduce our novel idea from the following aspects. Motivation. Firstly, embodied visual navigation has strong potentials of practical applications in the field of robotics. For example, the service robots are required to navigate to a specific object to help humans find what they need. However, there exists a problem that the training action space mismatches the testing action space when solving the embodied visual navigation task through learning methods. For example, when the robot performs rotate action, it can rotate 60 degrees during training, but rotates only 30 degrees during testing because of the different environment settings or the sudden failure of a specific sensor during testing. And almost no method is developed to solve this problem. So we propose a novel problem of action-insensitive embodied visual navigation task with different action spaces between the training and the testing process. Action-insensitive embodied visual navigation task. To solve the above problem, we propose a new task of action-insensitive embodied visual navigation, in which the training action space is different from the testing action space. The goal of this task is to find the specific object in as few steps as possible, with different action spaces during the training and testing process, using egocentric visual images and the class label of the object. Robust adversary training framework. We propose a two-stage robust adversary learning framework to properly adapt to new action spaces. The first stage is adversary training process. During this process, we build a model to learn a general feature representation of the state and obtain an optimal action decision strategy. The model is composed of three main modules. The feature extraction module is used to extract features of the environment and the target object. The action decision module uses these features to decide which action to perform for the next step with the actor-critic structure. The adversary classifier module takes the state features as input to find out which action leads to the current state. To ensure the generalization of the feature representation, we hope it's difficult to classify the action class, so the objective of the action decision module is to maximize the exploitation of the cumulative rewards, and the objective of the adversary classifier is to maximize the cross-entropy loss function of the classifier. The second stage is the adaptation training process. In this process, we modify the number of the output neurons in the last fully connected layer of the actor network, keeping other parameters fixed. Then we retrain the model in a subset of the training samples to learn an optimal action decision strategy that is adapted to the new action space. Experiments. The dataset is built from the AI to-store platform. There are 80 scenes for training and 40 scenes for testing from tab, kitchen, living room, bedroom, and bathroom. The training action space includes action move ahead, rotate right, rotate left, look up, look down, and down. The different testing spaces include the following four situations. The first situation is the testing action space is the subset of the training action space. The second is the training action space is a subset of the testing action space. The third is the intersection of training and testing action spaces is not an empty set. The fourth is The intersection of training and testing action spaces is an empty set. We conduct experiments in all these situations using the proposed model, comparing with other baselines. The quantitative results show that the proposed adversary learning framework achieves higher value of success rates and SPL compared with other basic modules without adversary learning. Next, we will show the qualitative performance of the proposed model compared with model without adversary learning in different action spaces. All these examples show that the proposed robust adversary learning framework can outperform other existing models in the action-insensitive embodied visual navigation task. Conclusion. First, we propose a novel problem of action-insensitive embodied visual navigation with different action spaces during the training and testing process. We propose a robust adversary learning framework, which includes adversary training and adaptation training process to learn a proper model that can adapt well to new action spaces. Besides, the experiment results demonstrate that adversary training can help the model learn a general feature representation, and adaptation training can guide the trained model to transfer to different action spaces. That's all. Thank you.